Hello everyone. In the previous lecture, I have discussed about the mechanism of shear resistance, Mohr-Coulomb failure criteria. So in this lecture, I am going to discuss the measurement of shear strength. So there are different types of tests by which we can measure the shear strength of soil. So the first one is the direct shear test. And direct shear test apparatus is mentioned in the figure. So why we call the direct shear test? Because directly we calculate the shear strength of soil. So what we do in the test? So you can see in the figure that there is a probing ring on the right side. In the probing ring there is a dial gauge. So by taking the reading of dial gauge which is fixed in the probing ring, we can calculate what are the load which is applied by the probing ring and what are the load which is applied, and that load can be a shear load, that can be load a vertical load. So now in this case you can see there is we have fixed the probing ring in the horizontal direction and we are applying a horizontal or lateral force on the soil, and the soil gets failed in shear, so we call it shear load. Okay, so the dial gauge reading which is fixed in the probing ring, so that will give the shear force. You can see there is other dial gauge reading which is fixed, dial gauge which is fixed in the center of the apparatus. So that dial gauge reading will give the horizontal displacement or lateral displacement of the soil sample. Okay, we will take the reading of dial gauge which is fixed in the middle of this apparatus and we can get the lateral displacement. There is other dial gauge also which is in the top of the apparatus, and that dial gauge reading will give the vertical displacement. That dial gauge reading will give the vertical displacement. So I will discuss in the brief that when we will discuss the direct shear test, how we are making the what is the procedure to do the test and what are the calculation, what are the observation, and how we are taking the readings. Like we are taking the reading of dial gauge, so how we'll get the shear force. We are taking the reading of dial gauge, so how we'll get the lateral displacement. So all things we will discuss. Second is the triaxial compression test. So by name you can get some idea. So triaxial compression test, we are applying a compressive force or compressing a stress from the three direction, like in x direction, y direction, and perpendicular z direction. So we are giving the stress. So and this test is important for all types of soil. We can apply in the all drainage condition. We can apply this. We can use this test, and this test also gives the accurate results. And one of the more advantage of this triaxial compression test. So in this apparatus there is a control over the drainage condition, and a device is attached to the triaxial compression test, and that device can measure the pore water pressure at any stage. Okay, and we can also draw the Mohr circle at any stage. Means in the direct shear test we can draw the Mohr circle at the only failure condition, at the failure stage, but in the triaxial compression test we can draw the Mohr circle at any stage. So that is one of the advantage of this triaxial compression test. And in this test also a specimen is free to fail under the weakest plane. Okay, so in the direct shear test you will see that the weakest plane, that is already mentioned, like in a horizontal direction, so I will fail in the horizontal direction, and the weakest plane and failure plane is also mentioned, that is horizontal, right? But that can be a drawback of direct shear test. Soil can be failed to the weakest plane. Okay, and in the direct shear test we have just fixed the weakest plane, like horizontal plane. So that is not true in some cases. So in triaxial compression test we have not fixed any weakest plane. So soil will get the fail along the weakest plane. So that weakest plane we can calculate later. Okay. Third is the unconfined compression test. So the unconfined, by name you can get some idea, like unconfined, there is no confining pressure. There is no compressive stress we have applied in the x and y direction, only the vertical direction. So we have applied compressive stress only from the top, and we can get the shear strength of soil. So in the unconfined compression test apparatus is mentioned in the figure. So you can see there is a probing ring, and that probing ring will get the vertical load which we have applied on the soil sample. And there is a dial gauge reading, which is fixed in the probing ring. So that dial gauge reading will give the vertical load. Another dial gauge also is fixed on the top of this soil sample, and that dial gauge reading will give the vertical displacement. So in this case, two things are important. We are taking the reading of two dial gauge. First dial gauge reading will give the vertical load, and second dial gauge reading will give the vertical displacement. Are you getting my point? Okay. Vane shear test. So this is the one of the very small apparatus we can say by using this test, and this test we can perform in the laboratory also, in the field also. Okay, sometimes there is no required to make a bore hole or all those things. Directly we can using the vane shear test apparatus, we can calculate the shear strength of soil. So this is the apparatus of vane shear test, and there is a blade and all those details I will discuss in the coming lecture also. So let's start with the direct shear test. A direct shear test apparatus, which is mentioned in the figure. So they have many components, so that you can understand by the line diagram. So some of the components are very important, like probing ring. So by taking the dial gauge reading, which is in the probing ring, so you can calculate the shear load which is applied on the soil sample. There is a vertical assembly also, so you can keep some load on that bottom plate, and that normal load will apply some normal stress on the soil sample. There is a second dial gauge reading that will give us the horizontal displacement or lateral displacement of the soil. There is a third dial gauge, and that taking the reading of third dial gauge will give us the vertical displacement. Okay. So in this case there is a shear box, and that size of shear box is a 60 mm into 60 mm into 50 mm. And that shear box is divided into two parts. So the upper half parts which is fixed with the probing ring, and the bottom half parts which is in the container, and that container is attached to the jack or gear jack. So there we can apply some horizontal load. Okay, so there that gear will apply, some jack will apply the horizontal load. Okay, and then we will take the reading of shear force taking the dial gauge reading in the probing ring. Okay, so this don't confuse with this. The top half part of this soil sample is attached to the probing ring, and the bottom of the half part is attached to the container. That container attached to the jack. Okay, and the porous stone is also placed at the top and the bottom of the specimen in the drain test or in the drainage condition. So generally shear box is made of the brass or gunmetal. It is either square and circular in plan. So most of the cases you will see there is a square inside. Okay, a porous board you can see in the figure. There is a pressure pad of brass or gunmetal also fitted into the box at the top of this to transmit the normal load. So why we are applying this? We will apply normal stress on the pressure pad. So by which a pressure pad we will apply the uniform normal stress distribution through the to the soil sample. Okay, so this pressure pad will uniformly distribute the normal stress, so that we can get the accurate result. So we can get the accurate result. So there is also a large container, and that bottom half part is we will keep in the large container. Okay. So let's discuss the how we will conduct the test and what are the criteria. So specimen soil specimen of the size 60 mm into 60 mm into 25 mm. So what was the shear box size? Shear box was size 60 mm into 60 mm into 50 mm. So the soil specimen of the size is half of the shear box. Okay. So dial gauge reading is fitted to the container to give the shear displacement or horizontal displacement. Okay. The other dial gauge also is mounted on the loading yoke to record the vertical displacement. So we have seen in the figure also. The normal load is applied to give the normal stress of 25 kN per meter square. Shear load is then applied at a constant rate of a strain from the zero. So we are giving the shear load by the strain control device. Okay, already have discussed in the previous lecture also. Okay, there is two types of control devices: strain control and stress control. So in this test we are using the strain control device. Strain control device means the rate of a strain is fixed. It means rate of horizontal displacement or rate of lateral displacement is constant. So normal load we will apply 25 kN per meter square. You can apply some other value also like 20, or you can take the other value also. But for now you are applying the 25. And then you are increasing the shear load from 0 to the failure stage or 0 to the peak value. But in some of the type of soil, in case of the loose sand, you cannot get the peak value. So in that case, you will take the value of shear stress at the 20% of shear strain. So for soil which do not a peak point, the failure is assumed to have occurred a shearing strain of 20%. That is very important. This is very, very important, because in the most of the soil, loose soil, you cannot get the peak value. In dense soil, you can get the peak value. So there is no any confusion. But in the case of that soil where you cannot get the peak value, so what value will take? Where you will assume that failure is occurred? So we will assume occurred is happening at the 20% of shearing strain. And the reading of probing ring and dial gauge are taken at every 30 seconds. So we will take the reading of both the dial gauge at every 30 seconds. So a shear strain is equal to the shear displacement delta H divided by the length of the specimen. So obviously strain is a change into weight by the original length. So change in the length we can calculate by dial gauge reading. So whatever the delta H, we can calculate the by using the dial gauge reading, and total length already we have, so we can calculate the shear strain. Okay, so we can calculate the strain in the both direction, like in horizontal direction or in the vertical direction also, right? Because we have fixed the dial gauge reading in the both direction. Again, we are taking the horizontal displacement also, we were taking the vertical displacement also. Shear stress is obtained from the shear load indicated by the probing ring and the cross section area, obviously. Normal stress also we can calculate by dividing the normal load divided by the area. So we can calculate the normal stress. So are you getting my point? We have, suppose in the whole apparatus there is a 3 reading you have to take. 3 dial gauge reading you have to take. The first dial gauge reading which is fixed in the probing ring. So that dial gauge reading will give us the shear load. Second dial gauge reading will give us the horizontal displacement or lateral displacement. Third dial gauge reading will give us a vertical displacement. Okay. So we can calculate the shear strength parameters, that is C and phi, cohesion intercept and angle of internal friction. Suppose we have draw a diagram like horizontal axis is sigma axis, normal stress axis, and vertical is the shear stress axis. So in the lab or in the apparatus we have take the sum of the normal stress. So in the we are fixed some value like sigma 1 normal stress, that is maybe that can be 25 kilonewton per meter square, and we are performing the test, so we can get the failure of soil at the shear stress tau F1. Failure of shear stress at failure for the first stage, okay, for first sample. So suppose we have taken the 3 sample or of same soil. We have taken the 3 sample of same soil. Okay, so what we can do? We can take the other sample. Again, we can apply some other normal stress. Okay, and that is suppose that is sigma 2, and we will perform the test. We can get the shear stress, that is tau F2. Okay. Again, we will perform another test. Okay, or in the all the 3 tests which are we doing in the laboratory. So all sample will be same. All sample will be same. Okay, so that's why we can correlate with each other. Okay. So suppose this time we have fixed the different other value of the normal stress, that is sigma 3, and we have on the test, and we can get the tau F3. Okay, so we have 3 coordinate. By using the 3 coordinate, we can draw a straight line. So we have drawn the straight line, and that straight line we call a failure envelope. That straight line we call a failure envelope. So now we can calculate the vertical intercept of tau axis or shear stress axis. So that will give us the cohesion intercept, and whatever the angle of from the horizontal, that will give us the angle of internal friction. So we can calculate the phi. So in the coming lecture, I will discuss like how we are applying normal stress, like what is the sigma 1, how we are applying the sigma 1, and how we are getting the tau F1 value. Okay, in the single test, we'll do the same test. Okay, but different soil sample means the same soil sample. Okay, so how we will apply the sigma 2 value, and then how we are taking the sigma F2. So I will try to discuss whole in the details, and we will take the observation also. I will give some observation, and you can do the calculation, and you can make the same figure, and you can calculate the C and phi. So this C and phi is the shear strength parameter of a soil. Shear strength parameter of a soil. Are you getting my point? Are you getting my point? Okay. So let's discuss the. So the first question we have: a series of direct shear tests was conducted on a soil. Each test was carried out till the sample failed. The following results were obtained. So determine the cohesion intercept and angle of resistance or angle of internal friction, C and phi. See, this question you can solve by using the graph paper. So all these coordinates you have to draw on the graph paper, because the graph paper has a proper scaling. So all the data plot in with the proper scaling. Okay. So you can draw x-axis, sigma axis. You can plot a y-axis, shear stress on y-axis, that is tau axis, and you can get the 3 coordinate. Okay, and by using the 3 coordinate, draw a line that will be the failure envelope. So it can be it cannot be a proper straight line, but you have to draw a straight line. Okay, and that failure envelope will give us the cohesion intercept and phi. Are you getting my point? So this question you have to solve in the graph paper. I'm just discussing the procedure. So just plot the coordinate 1, that is 15 and 10, coordinate second, that is 30, 25, coordinate third for third sample, that is 45 and 32, and draw a straight line by passing all these coordinates. So it will give us the what are the intercept on the sigma tau axis, that will give us the cohesion intercept, and angle with the horizontal, it will give us the angle of internal friction or angle of resistance phi. So after plotting this question, making the question in the graph paper, or you can get the C value is 11 and phi is 26 degree. So from the plot we have C is 11 kilonewton per meter square and phi is 26 degree. So now we know that like shear strength of a soil, we have the formula like C plus sigma dash 10 phi. So now we have the C and phi, so we can put in this equation. So shear strength of soil, that is tau max, it's called to 11 plus sigma dash 1026 degree. So now in this equation you will put the value of sigma dash, you can get the shear strength. Okay. So in the lab also you can do this test. So what you can do, for the fourth sample you can put the normal stress and you can put in this equation and you can get the shear strength by analytical, and you can do the after conducting the test you can get the shear strength also. So you can calculate what is the shear strength of soil by analytical or by experimental. So you can check the error on all those details. Okay. So these are the reference that I have taken, and in the coming lecture I will give you some link of direct shear test. So in that video you can watch, and you can watch how they are doing the test of direct shear test, and how they are taking the observation, how they are doing the calculation, how they are making the graph, and what are the conclusion what are the conclusion and what are the discussion they are talking about the results. Like some result are came, so on the basis of result, what you can comment on the what are the type of soil and what are the condition of that soil. So all those details you can get. So thank you.